Oh, we are live now. Hello, developers. Good night, good evening, good afternoon. I am João. I will be your host today, and today I am with the guy. Guy Rose works for Redis Labs as a developer advocate and has decades of experience in writing softwares and stuffs. And he is with us today to talk about the mystery machine learning. Hello, guy.
Howdy, how y'all doing?
Yeah. So just
I
to
decided to go in with my cowboy introduction, by the way.
yeah, you just look like a cowboy.
Yeah. With the Viking hat in the background, right? Yeah.
Yeah, that's it. Just to make the announcements for developers, we are starting now the Redis month, and it's gonna be awesome. We have this partnership with Redis Labs, the home of Redis, and we will have contents about Redis with the Redis guys. So it will be the best person to. Oh, I just got the Jadestival comment. Hey, Joel, this channel has only SMS and him. Hey, guy, and he is right. Just
Howdy.
a little joke to Julia Silva. You will not ask for monads today, right?
No.
Uh,
Well, I mean, just
in the
likes
last,
and subscribes. Yeah.
yeah, in the last months, we talked about functional programming, and in every session he asked about monads. But that's okay. People just smash the like button, ring the bell, and share with your friends. And now we will go with this amazing guy doing his show. So it's up with you, guy.
Thank you very much. So, welcome everyone. This is my talk, Mystery Machine Learning. I'm hoping you're all fans of Scooby-Doo because this is a Scooby-Doo themed talk on recurrent neural networks, on neural networks in general, recurrent neural networks in specific. And I'm going to talk a little bit about Redis AI as well. And I got a demo showing how it all works. Great question, by the way. Ask questions. And I'm watching chat now. So if you have questions, go ahead and leave them there. And I will try to keep my eyes on chat. I might miss something, but I'll try to answer them if I see them. And if not, Jono's he's gonna interrupt me and give me the question as well. So that's totally cool as well. So yeah, ask away. So, excuse me, as I touch my nose. Yeah, so mystery machine learning, Scooby-Doo. So my name is Guy Royce. I'm a developer advocate at Redis Labs. This is all my social media stuff. The thing that I want everyone to do is to look at my Twitter ID and give me a follow so that I can feel better about myself because of the number of people that follow me on Twitter. But the thing that you probably actually care about is the GitHub link there at github.com/Guy Royce. That link will take you to a bunch of repos, including a repo containing these slides and all the sample code I'm going to show you tonight. So, I'll have a link to that again later on. But that's the one link you care about. I do work for Redis Labs, and this is Redis Month, and I'm pretty excited about getting to be a part of making this happen. You've probably heard of Redis. You may not have heard of Redis Labs. Redis Labs is, well, it's the home of Redis. We fund a significant portion of the open source development of Redis, and so we like to let people know that, hey, we're out here and go out and give talks in the communities and help support the communities that use open source Redis and the Redis Enterprise versions as well. So that's who I am. That's where I work. Yeah, enough of that. Another thing about me that's really important is these letters here. I always like to have people try and guess what this stands for. It stands for something. But it doesn't work. It works better in person than it does over a stream. So I'm just going to tell you what this stands for. It stands for I am not a data scientist. So I'm going to give a talk on recurrent neural networks and neural networks more generally as well. But I'm not a data scientist. I don't have a background in data science. I'm not even particularly mathy. I am just a fan of data science. I like machine learning. I like deep learning. I think it's a really interesting topic. And so I go out and I learn what I can about it, and I put together talks and I share what I've learned. What this means is that I don't have all the answers, and I might even be wrong in a few points. But I might be a little bit wrong sometimes on things. Data scientists get in there and say, well, technically this thing here, so they're technically correct, which is the best kind of correct. But the thing I do is I try to bring a developer perspective on the data science and try and understand this in an intuitive way so that I can explain it to other developers in an intuitive way. So that's that's my little caveat, my little warning that says, I'm going to talk to you about data science things, but I'm not a data scientist. I just get excited about these topics. The other thing that I am is I'm an enormous fan of Scooby-Doo, and I have been watching Scooby-Doo literally my entire life. And I am a middle-aged man, so I've been watching Scooby-Doo since the 70s. And what I always liked about Scooby-Doo is that it was always there's a mystery, and everyone assumes that it's some supernatural ghost. It's like it's the ghost. It's at the amusement park, or the ghost at the haunted house, or whatever. It's always some supernatural ghost or monster. But what they find out in the end of Scooby-Doo is that it's not a ghost, it's not a monster, it's just a man in a mask. And I think data science is kind of like that, where we look at these things and we think that they're kind of magical, like they're, like they're a magic brain in a box. But they're actually completely knowable. They're actually quite mundane. They're math and nothing more. They're just math at scale. And so I like that about Scooby-Doo, and I like that about machine learning. And what we're going to do tonight is we're going to do a fun and sort of ridiculous problem. We're going to use a recurrent neural network to tell us who said, we'll give it a line from a movie, a Scooby-Doo line from the Scooby-Doo movies or the Scooby-Doo cartoons. And we're going to build a model that will tell us who said it. Was this said by Velma or Fred or Daphne or whomever? And so that's what we're going to do tonight. We're going to figure out how to determine who said what in Scooby-Doo using data science, using a magic brain in a box. No, using a man in a mask. And to do that, we're going to build a little application. And that application is going to take this data set I have. It's a very simple data set. It's a CSV file. The first column is who said it, and the second column is what they said. So, Scooby said, "Okay, Reggie," and Shaggy said, "Look out, Scoob," and Velma said, "Jinkies," right? These are their catchphrase, the things that they always say. We've got a data set full of those. We're going to use that data set to build a model, a neural network, a recurrent neural network. And then we're going to take that model and we're going to deploy it on Redis using Redis AI. And then we're going to take that model deployed in Redis AI and build an application on top of that. And then we can ask that application, who said it? Was it Daphne or Fred or Scoob or Shaggy or Velma? So that's what we're going to do tonight. To learn all the things we need to learn to do this, we're going to cover a few topics. We're going to go into neural networks. I'm going to talk about how neural networks work in general. And get down to the individual neuron level. We'll touch a little bit of math, but nothing heavy, just some basic arithmetic, nothing, no calculus or anything like that. We're going to look at recurrent neural networks in detail and how they differ from a generalized neural network. We're going to look at Keras, which is a framework, Python framework for building neural networks. It's a domain-specific language that makes building neural networks easy for developers to do. And finally, we're going to take a look at Redis AI to see how we can all this stuff works. So let's start with the neural networks. A neural network, you've probably seen a picture like this before, where it shows sort of the layers and the connections. This is a neural network. This is what's called a fully connected neural network, because each layer in this neural network, like right here, this layer is connected to this layer, which is connected to this layer in all the ways that they can possibly be connected, in all the permutations. And it's got an input layer, which are the numbers coming in. It's got a couple of hidden layers. And so each layer passes those numbers from that first layer to every node in the next layer, and then to every node in the next layer. And they compute new numbers and keep passing them on and chaining them out through the hidden layers until you get numbers in your output layer. And what these do is they take numbers in and they give us numbers out, which is a function. Neural networks are functions. And in particular, these functions are used to draw lines. So this neural network here is a function that draws a line. That line can be used to do a couple of things. We can use that line to classify things, to put things into a categorical space by separating the space the line is drawn in into categories. So hot dog, not hot dog. If you're on one side of the line, it's a hot dog. If you're on the other side of the line, it's not a hot dog. And so this line is dividing that. And the further away from the line you are, the more sure you are you're in that category. The closer to that line, the less sure you are. So you can use these lines to do classification. You can also do these lines to predict a number or do regression to get a continuous value. So here we've got a little chart that's showing the number of Scooby snacks required to overcome a particular spookiness level. So, you might have a spookiness level 2. How many Scooby snacks is required to overcome that spookiness level? And so what we do, instead of figuring out what side of the line a point is on, we figure out where on the line the point intersects. So we give it a coordinate. And here we say we got a spookiness level of 2. And this corresponds to a 2 Scooby snack sort of situation. So I need 2 Scooby snacks. So I'm able to find a number on that line. These are 2 ways that we can use these lines that are being drawn by machine learning and by neural networks. Now, to understand how these things work a little bit more well, to understand them better, let's look at a simple neuron. Let's look at just the simplest neuron that we can possibly have. The simplest neuron would take in a single value, an input, output a single value. Now, neurons typically take more than one value in, but let's do a simple one just so we can understand how they work. And so you can tell already this also draws a line. This is actually a function as well. You give it an X, you get a Y. If you put a bunch of numbers in, you can get a bunch of numbers out. You could draw a line. You could plot that out. You could graph that. Inside of this neuron, we've got some values that modify how the function behaves. So we've got a weight, which is multiplied by the input, and we have a bias, which is added to the result of that multiplication. So our neuron has an input, an output, a weight, and a bias. These weights and biases are calculated using a bunch of calculus that, quite frankly, I don't understand. But I know that I can say model.fit in my code, and it works, which is the proper developer response. And so the math for this turns into this very simple formula. The input times the weight plus the bias will give us an output. And if you are remembering your algebra from way back when, you might recognize this equation. This is y equals mx plus b. And where y, our weight is the slope of our line, and the bias is the y-intercept of our line. And so what a neuron does is it draws a straight line. And those straight lines can, have lots of different angles, and you can slide them to the left and right by adjusting the y-intercept, and by adjusting the slope or the weight in the neuron, you can pivot them. You can rotate them. And this will let us draw any line we want. And then we can use that line to make a prediction, right? You can, just like we did with the Scooby snacks and with the hot dog, not hot dog. But sometimes we don't want our lines to be straight. We want to adjust that output before we do it. And so our neurons can contain a function inside of them. They can have an activation function, where they take the input times the weight plus the bias, and they run it through a function before they output it. And so we have a neural network, which is a function, made of neurons, which are functions, which actually have a function inside of them as well. That's functions all the way down. And so the activation function can take that linear output and transform it into, for example, a sigmoid, where we go from a value that approaches 0 and approaches 1, but never reaches either of those, and has an average or a middle value of around 1/2. And so this allows us to, for one, make sure that all our numbers are positive, and to constrain sort of runaway values. And so this is one activation function that can be used. Another one is to use hyperbolic tangent. Hyperbolic tangents will allow you to scale from -1 to 1. They're basically like a tall sigmoid. And this is another common one, but by far the most common activation function that's used is the rectified linear units. or ReLU, which is way simpler than it sounds. ReLU basically says either use the number. If the number is greater than 0, use the number. Otherwise, use 0. That's it. Max y comma 0. That's all it does. And this tends to work best for neural networks, and I'm not exactly sure why. It's the one that tends to work best. And I think what it is if you think of the metaphor of a synapse in your brain firing on these neurons in a neural network, this allows the synapse to fire in one direction, positively but never negatively, and allows it to fire softly or very hardly, gently or with much ferocity. And so this allows you to kind of crank those numbers up. One of the problems you have with Sigmoid is that as numbers get bigger and bigger and bigger, they tend to, you have to keep pushing those weights to more ridiculously high values, and the calculations just get wonky. By using this, you can, your weights and your biases don't have to get so ridiculously large. And so that seems to help out quite a bit. A more realistic neuron would not be one that has a single input, but would have multiple inputs. So this neuron here has 3 inputs, x0, 1, and 2. Of course, I'm going 0-based because I'm a programmer, and all good programmers do 0-based arrays and good programming languages, with the exception of R, which is 1-based. And Visual Basic, I believe, was 1-based as well. But all this is doing is drawing a slightly more complicated line. Yeah, it's not even drawing a more complicated line. It's drawing a line through a plane, or it could be drawing a hyperplane through a hyperspace. So the idea is you could have more than a 3-dimensional space. You could have a 10-dimensional space or whatever. This is a 4-dimensional space, and so these x, y, and z are determining a hyperplane that bisects a 4-dimensional hyperspace. But it's doing that same thing that it's doing with the line. It's just scaling up the dimensions. A perceptron network is not composed of just a single neuron. So thanks for the question. A perceptron is actually where the activation function came from. The idea with a perceptron is that you would hit a magic number and then it would fire. And so once you got that to a particular value, it would overcome a threshold and then activate. That's actually why they're called activation functions. It's because in the perceptron, your activation function was determining, am I past this threshold or not? But a perceptron network is made up lots and lots of neurons, just like any other neural network. But it has to do with the activation function being used. And perceptrons kind of fell out of favor. They're just where we started. So the great question, because it let me talk about where the word activation function come from. So thank you. But so here we've got, 3-dimensional hyperplane bisecting a 4-dimensional hyperspace, but it still works the same. We're just adding them together. So it's the sum of the weights times the inputs plus the bias. And so to get a little mathy here, we can use a sigma to show that math happening, where we're saying for all the values that are input, multiply the weights times the biases, sum them all up using the sigma and plus b. It's just mathematical shortcut for the previous statement. So that's the function, that's the arithmetic that's happening inside of a neuron, inside of a neural network. And then we create arrays of these and networks of these neurons, hence the name neural network. And we get a function full of functions, full of functions. And this allows us to draw not straight lines, but all kinds of interesting and curvy lines, so that you can draw interestingly shaped lines and say, well, what side of this line am I on? Where on this line am I? And do that whole regression and classification operations that I showed earlier. So that's sort of a, 15-minute introduction to neural networks. So there you go. How is a neural network different from a recurrent neural network, though? Well, a recurrent neural network is using all these same principles, but it's managing its input and output a little differently, and it's configured differently. It's set up differently. So here we have our input layer, x0, 1, and 2. I've got these represented here as single neurons, but they're really arrays. They're tensors. They're arrays being input for each input here, or they can be. They don't have to be. And then you've got your output layer, which is again represented in a similar fashion. So we got 3 X's and 2 Y's coming in. 3 X's coming in, 2 Y's going out. But the hidden layers are configured in a unique way. These hidden layers are the same fully connected neural networks that we saw earlier in a fully connected neural network. But they have, their output doesn't always go to the same place. And so what we have here is the first input here, X sub 0, goes into this first hidden layer. Its output will then, it has an output which we can grab this way if we want, but also goes into the next set of hidden layers. And it has an input and the previous one. And so this creates sort of a context or a history that the neural network becomes aware of. And so recurrent neural networks are specifically good at dealing with ordered data or chronological data or data that has a natural sequence. It doesn't have to be a time series, but that's one of the most common scenarios for it. But it's a thing that has a natural order. And where the order has meaning. I think that's probably an even better thing to point out, is where that order is meaningful. And so what this does is this hidden layer here sort of comes to conclusions based on the first input, and those conclusions are input into the next input. And so this might be like stock prices over time. It might be words in a sentence. It might be it might be an image. You might just have one of these as an image. And then your outputs are similarly chronological in nature as well. And you can configure these in a few different ways as well. So this is it's the same thing happening, but it's just structured a little bit different. It's got that chronology to it. You can create these in many-to-many, many-to-one, and one-to-many structures. Many-to-many has many inputs, and it has many outputs, which is why it's called many-to-many. And for example, you can use this for translation or chatbots. So you give it a sentence in, and here's a sequence of words. And so here we're going to build like a Scoob bot where it says things that Scooby-Doo says. So Shaggy says, "Look out, Scoob." And then Scooby's like, "Okay, Raggy." And so it's got a response, right? Shaggy said a thing. Scooby responded. The Scoob bot responded. Many-to-many. This is, chat bots. We can use this for translation. We could put English in one end and get Portuguese out the other. And these are things where the order matters, where the order has meaning. You can do one-to-many. One-to-many is particularly used for captioning pictures. So you can give it a picture. You can actually run a picture through a convolutional neural network and get an idea of what's in that picture, and then feed the output of that convolutional neural network into a recurrent neural network, and then it will generate a caption. So here we're going to pass in a picture of Daphne, and it's going to come up with something that she might say. So here it's concluded that this picture should be captioned, or Daphne would say, "Jeepers, they mean business." And then many-to-one is often used for classification of text, or you could use it for predictive text. So you could put in and say, I just typed in these 10 words. What's the most likely word I'm going to use next? Actually, you can use many-to-many for that too and get like a couple likely words to be used next. Or you can just have an array as an output as well. But so you can use it for predictive text, you can use it for classification, you can use it for sentiment analysis. Is this text message that I've received here, give me a number from 0 to 1 as to how positive or negative that response is. So this is many-to-one. So here we are. We can give it some text and say, hey, let's split up. Now, who says, hey, let's split up amongst Mystery Incorporated? Well, that would be Fred. He's the one who always thinks that Shaggy and Scooby and Velma should go off in one direction, and him and Daphne should go off in the other direction. So many-to-one. Many-to-one is the one we're going to look at tonight. To look at these in greater detail, we're going to look at classifying text for Scooby-Doo, like I said at the beginning. So we will pass in the phrase, "I can't see without my glasses." And we will learn that is indeed Velma that says she can't see without her glasses. And so that's the problem we're going to solve. The first thing that I think is worth pointing out here is I started out talking about how neural networks are just math, and you're just doing numbers. You got numbers coming in, you get numbers out, and it's just drawing lines and all that kind of stuff. But this is totally wrong, right? We've got words here. These words aren't numbers. And, So we need some way to take these words and turn them into numbers. And we've got Velma as an output, and I'm pretty sure Velma's not a number. Maybe the government sees her that way, but Velma certainly doesn't think of herself as she's a person, right? She's got a name. And so we need to turn these things into something that machines can work with, that neural networks can work with. And so how do we do that? Well, let's look at the input first. So to turn the words into numbers, we use a process called tokenization, or tokenizing. To tokenize these words, it's basically, we take the entire corpus of text that we have, all of the words we want the model to learn from, and we just count all the words. And then we take the word that's most common, and it's number 1. And the word that's second most common, it's number 2. All the way through to the next highest word. So I've got a small little body of text here. And so Jeepers, all right, let's go. Just a few lines from Scooby-Doo. And I've counted up these words. And if you want to check my work, I've actually done all the math. So this math is all correct. And so the most common word is like and raggy. And so I picked like first because it's alphabetically first. And so that becomes 1, then 2, then 3, then 4, all the way to 24, which is zoinks. So we create a little cipher. It's like that substitution cipher you do when you're a kid, where A is 1 and B is 2 and C is 3 and D is 4. We just assign the letters to numbers, and you're just saying, okay, well, whenever I see the word Jeepers, then that is 12. And so that's the first step in tokenizing them. We build this dictionary by counting all the words, and then we just turn the words into numbers. And so I can't see without my glasses turns into 10, 8, 21, 23, 4, and 3, because glasses is word number 3, and without is word number 23. Boom. Instant numbers. Easy peasy. However, this is also missing a word. And so how do I take this missing word and turn that into a number? Well, it's easy. It's 0. It's null. There's a missing word there. And so it's null. And null is 0. You might have noticed back here, I started with an index of 1 and not an index of 0, even though I kind of joked about how I always start with an index of 0 because I'm a programmer. Here we started with a 1. And we do that because any word that we don't know, like if we run into a word that's not in our dictionary, or if we have a word that's not there, because not everything is going to be 7, not every bit of text we want to classify is going to be exactly 7 words wide. We need to be able to handle nulls. So we put a null in there, null becomes 0, and so null, I can't see without my glasses, is the same thing as before, but it's prefixed with a 0. You might have also noticed that I write justified everything in it. I did that for a reason. I'm going to answer that a little bit later. So the next thing we do is we're going to take these, our array of words, our tensor of words here, 0 through 3, our tokenized words, and we're going to one-hot encode them. And so one-hot encoding says, take all the classes of things, all the words in our dictionary, and word number 1 is column number 1. And word number 2 is column number 2. And word number 3 is column number 3, all the way out to word number 24, which is column number 24. And then we put a 1 in the column that corresponds to the word that we need. And so now, instead of having a one-dimensional array with just words in it, we've got a two-dimensional array, or a two-dimensional tensor, or I guess a matrix, with a bunch of full of 1s and 0s. And now we can take each of these matrix entries and run them against an embedding. And so for each entry here, we can take like the 1 for glasses right there, and we can get a row for the embedding, and that then represents that word in the machine learning. The embedding, here are the rows of the words. The embedding sort of has a semantic understanding of what that word means in context. So if we look at like the column where we have glasses, glasses is going to be 1, 2, 0, 14, 75, 0. But each of these columns sort of embeds a meaning. So this column here, where there's a big number here, it means glasses more than, say, column 3 does, where there's a 0. And so where the numbers are large, there's a similar meaning. So, I mean, these are just random numbers, but so looking at this, 92 and 75 are kind of big. And so like and glasses are semantically related in meaning, even though they're not really semantically related in meaning. But this might have the idea of things that are lost, or maybe things you put on your face, whatever the network figures out. But this semantics is part of this, and with Keras, you just say, "Build me this thing," and it does. And so I don't really have to think about it a ton, but that's the idea here. And so this gives us sort of a meaning for this word as opposed to the word itself. Because we might say spectacles, I can't see without my glasses. Spectacles and glasses would have a similar number, and so the model would treat them similarly. And so what we're really inputting here is several one-dimensional tensors. So null is all zeros. Here's the value for I, and can't see without my glasses. So this is how we transform that input to be something that this recurrent neural network can understand. What's really being output? Well, we're not outputting Velma. We're outputting a number. And actually, we're outputting a tensor of a one-dimensional tensor of numbers here as well. So here we've got 5 numbers, and one's really big, and the rest are kind of small. And if you look closely, you'll see that they all add up to 1. And so what these are they are positions for the different classes that we have. This is sort of the reverse of the one-hot encoding. Each column here represents a character in Mystery Incorporated. And so since these add up to 1, we can treat them as percentages. And so this model predicts with 83% certainty that is Velma, and 11% certainty that it's Scooby-Doo, and then single-digit certainty for the rest of them. So numbers in, numbers out. There is a problem with recurrent neural networks, and this is actually part of the reason as to why everything's right justified. It's called the vanishing gradient problem. And the problem is that each hidden layer here gets half of its input from its input and half of its input from the conclusion of the previous chain. And so that means half of this decision is the word glasses. And so you can easily get models that will fixate on the last words, which actually, as we'll see, my models do. Because Velma tends to say the word, I can't see without my glasses. Glasses, the model learns that glasses is the important word, and it ignores everything in front of it. And so here, half of the decision is that word glasses, and half of it is the summation of everything that came before it. And then of the my prediction, half of that is the my, and half of that is the summation of everything came before that. And so this means that words at the beginning keep getting cut in half as far as their importance. So the glasses is half the prediction, my is a quarter of the prediction, without is 12.5% of the prediction, C is 6.25%, et cetera, et cetera. So things to the far left don't have a lot of importance, and things to the far right have too much importance. There are ways of solving this using LSTMs and GRUs and also transformers, which is a lot of the direction where natural language processing is heading right now. And they set up ways of it fixating on certain words and saying, no, this word's important, remember this. So that's how these tend to work. I haven't looked into those in great detail, but be a good exercise to go find out how they work in greater detail. So that's sort of recurrent neural networks in a nutshell. Let's take a look at the thing that we're going to use that makes this all easy for us developers to do it, and that is Keras. Keras is a domain-specific language that makes writing neural networks easy. You can just write neural networks in the terms of neural networks without having to worry about any math. It is written for Python developers. So if you want to use Keras, you're using Python, and it's part of TensorFlow. It wasn't originally, it was its own project for a while, but it's merged with TensorFlow 2.0 and forward now incorporate Keras. It's actually pretty straightforward to use. This is all the code you need to build and train a model. So the first thing you do, you say model equals new sequential. Sequential is the type of model it is. It means not in terms of recurrent neural networks, but saying it's a layer followed by another layer, followed by another layer, followed by another layer. So it's sequential. You define your layers using just words, syntax that is thinking in terms of layers. So model.add, and we add a dense layer. That'd be a layer that's fully connected. You tell it the activation function you want to use. We want to use relu, and we give it an input shape of 4. And it's 4 comma because it's a Python tuple, and the comma tells it it's a tuple. And that's the input shape of 4 is saying that we have 4 input values going into our dense layer of 5 neurons. Then we can say we want a second dense layer with 5 neurons, also with an activation function of ReLU. And then we have a dense output layer with an activation of softmax. Softmax says take the numbers that are output, make sure they add up to 1 proportionally so that we can treat it as a percentage. So this is told Keras how our model is structured. It has these layers, they have these number of neurons, these are how they're connected, this is how they're activated. Then we call model.compile, and we pass it an optimizer. An optimizer is the thing that figures out and adjusts the values for the weights and biases that are inside those neurons. So the W's and the B's, the slope of the line that they will draw, and the shiftedness of that line, or that hyperplane, really. The loss function is how we figure out how wrong the model is, how far off those weights and values are. We're using categorical cross entropy to do that because we're doing classification. Atom is the optimizer we're using. It's a type of stochastic gradient descent, which are words that I've learned how to parrot and don't fully understand what they do. I know that it's using some random values. That's the stochastic part. It's gradient because it keeps cutting in half smaller and smaller. And it's descent because it's trying to get to a low value in the bottom, but I don't know how the math itself works. I just sort of understand vaguely the principles of what stochastic gradient descent does. But that atom is a variety of stochastic gradient descent. The categorical cross entropy is our loss function. And then we, for metrics for us humans, we have an accuracy, which is just a straight up percentage accuracy. And so we say compile this model using these things. Once we've compiled it, we can then train that model calling fit. We pass in our training data. X is our inputs. Y is our expected outputs. We give it a batch size, which says go through 20 records or entries, and then calculate the loss and run the optimizer. And then epochs of 10 means go through the data set 10 times. So in groups of 20, go through the data set 10 times, retraining as you go. Once we've done that, we've got a trained model. We can evaluate that model, giving it some test data to verify how our training worked. And then we can start making predictions with various inputs. So that's all the code for defining a simple neural network. A simple RNN actually is less code, which is kind of funny in a way, because we instead of creating these dense layers and those things, we create an embedding. That's that embedding layer that I showed you earlier. And we create a simple RNN. And we pass in the inputs and outputs of how big and wide these things need to be. And then we can add a dense output layer. I want 5 neurons with a softmax activation because I want to know if it's Daphne, Fred, Scooby, Shaggy, or Velma. But again, this is dealing in terms of recurrent neural networks here. So let me demo this here. I've got some code. I can show you some code here. I've shown you code already, but let me show you some more code. My cursor over here where it belongs. Yeah. And here's my Scooby-Doo data I was talking about earlier. Here's Shaggy Rogers. What a great idea, Scoob. I've always wanted to fly an all-you-can-eat airline. It totally sounds like something Shaggy would say. Maybe later I'll take that survey. So here's my data. I've got a little model building script here. And I'm just going to go ahead and run this real quick here. I've got Redis up and running already. Python's ready to go. So if I say, if I run this build model.py, it's going to go through and it's going to do all those things that I showed you earlier. This code's a little bit longer than that because it's doing a little bit more. It's well commented, so you can take a look at this later. I don't want to go through it too deeply. A lot of this is using pandas to take that data and put it in the right shape and transform it, and tokenize it and all those things. But the key thing here is when I run it, it actually runs. He said as it sits there. Ah, there we go. Right. So it's going through here, and you see my loss function here. The number's going down. That's good. My accuracy is going up. That's good. It's looking good. I'm up at 94% accuracy. And then I make a few predictions using the models. And something sad happens here. My accuracy is at 94.5%, 94.59%. And then when I run my test data against it, I find out that it's actually at 37.87%. So my accuracy is terrible. This is a classic example of a model being overfit. And this is why you always work with the data scientist when you're trying to make models. Very, very important. But it still works fairly well here. So my test predictions in the code here, I give it the word Jinkies, which is a 153, and this is all those zeros to the left of it. This is our input into that RNN. And it gives us a 68% certainty that that's Velma Dinkley, which that is totally something Velma would say. Like hang on, Scoob would be something Shaggy would say. And it does say with a fair degree of certainty that that's Shaggy. And Roque Raggy is definitely something Scooby would say. And it is 89% certain that it's Scooby. So my little bit of code here works. A lot going on here. We can look at the code a little bit if y'all would like to see it. A lot of this is just converting the data around here. So we're go up to the top here. So here we've got we load a data frame from up here. This is us loading our CSV file, and then we're separating out into the features and the labels. The features are the lines that the character says, and the label is who said it. And so this would be like look out Scoob, and this would be Velma, you know. And then we need to take the labels and encode them. So we use a label encoder, give it the labels, and it will say, well, it'll say that Daphne's 0 and Fred is 1, all the way up to Velma being 5 or 4. And we save that off as some JSON here because we're going to need that later. And then we can take our labels now that we have an encoder and encode them. So instead of having the names, we have numbers. And then we can one-hot encode them by calling toCategorical here. So it's doing a one-hot encoding of that. And then we do the similar work with our words. Here we got to tokenize them. And fit them on the text. Make sure that they're padded to the left with zeros. The text to sequences turns them to numbers. And then we save our word index. If we look at our word index here, here's our classes, right? Daphne, Fred, Scoob, Shaggy, so 0 through 4. Our word index is this word corresponds to this number. So it starts out at like the for number 1, which is a very common word, obviously. And at the very end, the last word is eyeballs, 2,172. So we got 2,172 words in our dictionary. Then this is that code that we saw on the slides here, right down here. Here I'm splitting it up and taking 80% of the data for training and 20% to test it afterwards. And here we're adding the embedding, and we're adding our simple RNN. Here we're adding our dense layer. We're compiling. We're printing a summary. We're building. We're training it. We're evaluating it. And then here I'm doing a few test predictions so we can, see it actually do a thing. So cool. And this code, like I said, is out on GitHub, so you can go check it out there. Let's go back to the slides. And again, if you have any questions, feel free to drop them in chat. So Redis AI is the next piece of what we're building here. What is Redis AI? Redis AI is it's a module that extends Redis to add AI features. So Redis has modules you can add to them to add new capabilities like graph databases and probabilistic data structures and time series and things like that. AI basically turns Redis into a model server. It allows you to deploy your models from multiple platforms onto Redis and then invoke them using Redis commands. And makes that nice. And it's Redis, so it's, of course, fast. And it's really easy to integrate with because lots of us are talking to Redis already. It can support models built by TensorFlow, which is one of the things we're using here, PyTorch, which we're not using here, and Onyx, which we are also using here. Onyx is the Open Neural Network Exchange. It's sort of a generalized or a standard model format that you can convert your models to, which is really cool because that means you can take models from lots of different backends, convert them to Onyx so that data scientists can pick and choose their tools. And then you can put them on Redis, and then anyone can call it from any language. And so it creates a nice layer of abstraction between Redis and or between the developers and the data science team. So I'm looking at a question here from Jose. Could you recommend a site that contains a deep learning topologies catalog like modelzoo.co? I've seen a great site, but forgot the name. There is one. I can't remember the name of it either, but there is like a neural network zoo. I might have a link to it at the end of the talk. I'm not sure. I know I've used it in other talks. I don't have it off the top of my head, but if you Google neural network zoo, I'm sure you'll find it. So,
if you remember that after the talk, we can put it in the comments, right?
yeah, absolutely.
Okay.
But I know it's called neural network zoo, and I could probably just, well, here, let's just do it. Let's Google it. Neural network zoo. Now you know I'm a real developer. I'm Googling things. Here it is. And I'm just going to add this. I got to put this in private chat. I can't actually access the regular chat, but there it is. So yeah, the repo is out there, github.com/GuyRoyce. So yeah, here's the neural network zoo. It's got different types of neural networks. This one's been out there for a little while. Lots of interesting ones out there. So many that I don't understand. I just haven't spent the time to research. But yeah, go and check it out. And we don't need to look at my work calendar. Okay, let's get back to the slides. So Redis AI, supports all these different backends. And it basically introduces two new data types to Redis. So Redis has hashes and sets and all sorts of things like that. It introduces a tensor, which are just multi-dimensional arrays of a particular type that you can just use as a data type if you want. But you can also use as inputs and outputs to the model. So you got a tensor and you have a model, which can be, again, a TensorFlow model, a PyTorch model, or an Onyx model. How it works is actually brutally straightforward. You load a model using ai.modelSet. You load a tensor using ai.TensorSet. Model set, tensor set. Makes sense, right? You call model run, and that says triggers an inference. It reads the tensor that you set, writes a tensor out for you, and then you read that tensor calling ai.TensorGet. And that's pretty much it. Here's the actual Redis commands if you're using the Redis CLI. So here we call ai.TensorSet. We give it a key for where we want to store it in Redis. We tell it the data type. So this is all the popular floating point and fixed width, our integer types that we know and love: floats, doubles, ints, bytes, unsigned integers, all those things. I'm using floats. Floats are the most commonly used in machine learning. And then you give it the dimensions or the shape of that tensor. This tensor is 2 wide and 7 tall, or 2 tall and 7 wide. It's 2 by 7, and it's got 2 dimensions. If it was 3 dimensions, we'd have a third number here. If it was 10 dimensions, we'd have 10 numbers here. And then we provide the values for that tensor just in order. And so here we've got the first, it's 2 by 7. So the first row is, this particular word I can't see without my glasses. And this is zoinks, like look out, Scoob. And so you can see how it's sort of arrayed there, pun not intended. And so that's how you set a tensor. To get a tensor, you just pass it the key. You pass it the word values. Hey, I want the values, the numbers of the tensor out. You can also pass in blob, and it'll give you a binary representation of that tensor. And then you can optionally ask for the metadata around that tensor as well. To get models with model sets, you can actually say ai.modelSet and pass in the values of a model, but it's just a bunch of gobbledygook binary string stuff. And so I always use Redis CLI directly with a -x. And what -x means is run this command that you see here against Redis, and then take the rest of the command from from whatever is being directed from input. So again, we're saying set the model in this particular key. This is a Onyx model as opposed to a TensorFlow or PyTorch model. This model will make predictions using the CPU and not the GPU. You can specify GPU as well. And we give it a file containing the model as a redirected input. So this allows us to set the model. To make an inference, we call model run. pass in the model we care about, the input tensor or tensors, and the output tensor or tensors. And so that is pretty much all there is to Redis AI. We can use this along with a bunch of code to build a fun little application where we can pass in the string roke-regi. Our application will hand that to Redis. Redis will hand that to Redis AI. Redis AI will push that into the model. The model will give us a result back to Redis AI, which will hand it to Redis, which will hand it to our application and tell us that the ScoobyDoo is who said that. So, time for my second demo. So this is where I actually take this model that I built earlier, the right here, that makes the ScoobyDoo predictions. The model files are sitting right here. I got an Onyx one and a TensorFlow one with it's a protobuf. And I've got Redis running already here. I think, do I have Redis CLI? Let's bring up the Redis CLI. I probably have run this earlier. I do a key star. Yeah, you can see here's my Onyx model and my mystery in, my mystery out, and my mystery TF. So I can do like a AI.tensor get mystery in, and then values and meta. And that will get me all the values in that. It gives me metadata about it. So I can, its data type is float, shape is 1 by 150, and here's all the values. I could just get the values, or I could just get the meta. Like there's the meta. I could get the blob, and you can see what it looks like as a blob. Right. So this is just the Redis commands I was showing you earlier. But let's go ahead and exit out of that. And I'm going to start up a little node application, a little express node application on port 3000. And if we take a look at this, it's actually going to use our word index and classes that I saved out earlier. And it's going to take just a post, and the post is going to have the string, the line from ScoobyDoo, and it's going to have whether we want to use the Onyx model or the TensorFlow model. So when it starts up, it's using IO Redis to talk to Redis. And so we get a Redis connection. We go ahead and load our blobs from the file system, our models. We call Redis to set the model here, right? Call Redis to set the TensorFlow model as well as the Onyx model. We go ahead and load our word index up and our classes. And then we have a handle request, which is actually the Onyx or the express request coming in. Whenever we get a request, we pull the back end and the line out of the body. And then we've got some error handling here. And then we encode the line. This is the most JavaScripty code. I love it. Where I lowercase the line, and then I have a regex that says only letters and numbers, get rid of anything else. And then I make sure that all white space is only a single character, not multiple characters. I make sure there's no white space on the edges. And I split the word on that single white space character, so now I have an array of words. And then I use the word index and map that word to their numbers using map. And then some of those will come back as undefined, and so I map all the undefineds to 0. So now I have a left justified tokenized sentence. Well, now I have a left tokenized, right, with the concatenating here. And then I call tensor set and model run. And so this will totally work. I would have to use Postman to do a post. I'm not going to do that because I wrote an application, a little JavaScript application that just talks to this little endpoint. And we're going to take a look at that. That's this guy right here. I refresh it. And so I can put in here a line from ScoobyDoo, and it will tell me who said it with my overfit model. So let's get a ScoobyDoo line. Anyone got a ScoobyDoo line? What's their favorite ScoobyDoo line? Which software do you use to open and visualize your model file? I usually use Netron from I didn't use any, actually. I have a model. So didn't use any tools to visualize that at all. That would actually be something fun to check out. So let's go ahead and put in a ScoobyDoo line here. Like, look out, Scoob. Who says that? That would be Shaggy, and the model does correctly. I can choose to use a TensorFlow model instead. It'll give exactly the same results. And so we can give another line. We'll say Jinkies. That's Velma. I can say let's split up Fred. So it goes through and oh, I'm totally going to give it a try. Totally going to give it a try. So let's split up. And again, I can use either of these models. It'll figure it out. But I mentioned the vanishing gradient problem earlier, and I can kind of show this in here. I can show two things here I think are kind of neat. One, I can give it words that it doesn't know. I can say like SpongeBob, who is totally not in Scooby-Doo. Look out, like SpongeBob. I can't see without. We'll go with SpongeBob. I can't see out my glasses. When I run that, it's going to say that's Velma. It doesn't know the word SpongeBob, but that's okay. It knows the rest of the words and is able to figure it out because this turns into a 0. And so this is sort of showing how it could fill in the gaps, which is kind of cool. And so it'll do things. It'll recognize things that it clearly has never seen in its test data, in its training data. But to show off the fact that it's the vanishing gradient makes things to the right more important, I can say like, I can't see without my glasses, Scoob. Now, who always ends their sentences with Scoob? That would totally be Shaggy, right? And so, but I can't see without my glasses is something that Daphne always says. So what's it going to do? It's going to say that Shaggy said that. Maybe it's looking at the like. So let's take the like off. No, it's still Shaggy Rogers. So this is an example of that vanishing gradient problem. The Scoob is half of the decision process at the end. And since the only person that ever ends their sentence with Scoob, or most often does, is Shaggy, the models overfit on that idea. So if we look at the run here, we can see this is the last run. I can't see without my glasses, Scoob. It was 95% certain that was Shaggy. And up here, like I can't see without my glasses, Scoob, it was 98% certain that was Shaggy. So it was very, very sure and very, very wrong and very, very overfit. So once again, this is why you want to work with actual data scientists and not just hack things together yourself as a developer. So that's my little working example of a ridiculous application that was a ton of fun to write, honestly. Thank you, Hanna-Barbera, for making my childhood great. Yeah, any questions so far? And anything that anyone wants me to use as an example for for the little app. I'll go ahead and copy paste it in. But anyhow, the lag makes it hard. Yeah.
Yeah. So far, so good. You can go on.
Cool. Okay. So that's pretty much my talk. I think you all should have a Scooby snack. We've covered neural networks. We covered recurrent neural networks. We looked at how to use Keras to build them in a very easy and developer-friendly way. And we've looked at how to use Redis AI to host those models and integrate them with an application. So I'm going to have a Scooby snack when I'm done, by which I mean ice cream. Here's some links to some of the stuff. Yeah, sure. Actually, I'd love to talk about it. So Redis AI is it's the thing hosting the model. So all of my my application is written entirely in JavaScript. So the thing that is going out and making that's using the model, all of my code is written in JavaScript. So if we go back to it's the wrong one. If we go here and look at my code, the only Python I wrote was my model building code. And then I just saved those off. So that was something that happened earlier, right? I don't have to care about that anymore. And my application itself is written in JavaScript all the way. So my little web client is obviously written in JavaScript because it's a web app, right? It's a web front end. It has to be written in JavaScript. I suppose it could be TypeScript. Yeah, but it's just going to transpile to JavaScript anyhow. So it's JavaScript. And then my Express backend is written in JavaScript. And so I'm able to use Redis AI as sort of a layer of abstraction between the data science work, which happened in Python, and the application development work, which happened in JavaScript. And so Redis AI gives me that sort of layer of abstraction and gives me a place to host those models. So the model's running on Redis AI. and I'm able to just talk to Redis using JavaScript code. I could have just as easily written this front end in C# or Elixir or Ruby or Haskell or whatever I wanted. Languages that don't have good data science support still have Redis clients that can talk to Redis. So I think that's the key thing that Redis AI is adding. Redis AI adds other capabilities. If your data is already on Redis, then you can actually just load it from there directly, and you don't have to make the network hop to get the rest of the data, so that can be faster. And there's other advantages. But the main one I'm showing here is just that abstraction that you get as a developer. Does that help? Or is that clear? And I know there's probably about 60-second lag, so as soon as I say I go on, it's gonna happen again. It's just the nature of the internet, right? Here's links to some of the stuff I played with here. The main one here is the code and slides. If you want to use Redis AI, you can check it out at redisai.io. No, I have not. I have not used either of those tools. Most of my data science work I've done has either been with scikit-learn or with Keras. So I think you've got actually more experience on this topic than I do, honestly, sir. But here's Redis AI. Here's our Docker image if you want to run this. Thank you very much. That's very, very kind of you, sir. Very, very kind. This is another list, I think, full of links. We've got a Discord server. I'm always on there, so you can ask me questions there if you have questions about this topic or others. Redis University has free classes on Redis. Nothing on Redis AI yet, but hopefully that'll be happening at some point. Lots of other Redis topics on university.redislabs.com. And we've got a bunch of YouTube videos at youtube.com/redislabs, many of them featuring me. So go and check those things out if you want some more Redis content. Of course, show up here Thursday for more Redis content as well. In case you didn't get any of those links, this QR code will link to the GitHub repo, which has the slides and all the code and everything that you can go and get all that wonderfully Scooby-licious stuff. This QR code is totally reliable. It will never give you up, nor will it let you down, nor run around or hurt you. It only goes to the repo that you see here. It totally will not rickroll you. Honestly, it actually doesn't rickroll you, but I'm so tempted one of these days to just put one in there. So go ahead and check that out. And yeah, that's what I've got. Thanks a lot. I'm Guy Royce, developer advocate, Redis Labs, and ranks, Raggy.
Okay, I just put your repo link in the comments in the case of someone being afraid of scan the QR code.
It'll never give you up nor let you down.
So we had a lot of interacting in the comments, and people said that was the best session that I ever had about neural networks, and I had to say that me too. Me either. That one of the best talks I ever had. So thank you so much. You just gave you a lesson after lesson, and that was so amazing. Thank you so much.
You're very, very welcome. I apologize. I think I went a few minutes over, but there's a lot of material in there, so we're at a little over an hour, I think. So
yeah, just 1 hour and 3 minutes, but that's okay. We can talk about it all night long if you want to.
Cool. Are there any other questions in chat, or do you have any questions?
Not yet. The first thing that I got attention was the Scooby laugh you just did.
What's that?
The Scooby-Doo laugh you did was so perfect.
Yeah. It's so my trick is, honestly, I have a formula, and that formula is introduction with a fun theme. Yeah. That's all I'm doing, right? So whether it's doing mystery machine learning for use ScoobyDoo to teach about neural networks, or whether like later on this month I'm going to be doing finding Bigfoot with Redis and Redis Search, and so I'm going to talk about Redis Search, and I'm going to use Bigfoot as a fun example because who doesn't want to find Bigfoot? That's I have a talk I did several years ago on convolutional neural networks, which was Viking themed. So it's just intro talk with fun theme. That's my formula.
Yeah, we will have another talk with you in the end of this month. About the Bigfoot you just said, and in the Thursday we have a talk with Elena. I don't know how to say her last name, but it's Elena.
I think it's Kolevska.
Yeah, so
I think
like
I've never actually said her last name with her present, so I could be totally getting her wrong.
Okay.
I'm pretty sure she's in Portugal, I think.
I'm not sure, but we will talk about scalability and high availability with Redis. So it's advanced content. So be tuned to learn more about Redis in this wonderful month.
Cool.
Okay. We don't have more comments, so you have anything more to say, Guy?
Just thanks for having me. It was a pleasure, and I'm going to go get a Scooby snack.
Yeah, me too. So thank you, everyone. Just share with your friends. Follow us in the social medias. We have our nicknames, and follow Guy on Twitter because he loves to see the number growing up. And that's it, guys. Thank you so much. And I think we are just closing the live now. Thank you, Yoda. Thank you, Joel. Thank you so much.